Hello, everyone. Welcome to VSA Online. It is 8 p.m. somewhere in London, and we start our regular session. And I'm very happy to host Paul Soulos today from Johns Hopkins University. And he will give us a talk about tensor product representation, well, as a general topic, but he will introduce concrete topic himself in a few seconds from now. So, Paul, please, the floor is yours.
Great. Thank you for inviting me to give a talk at this lecture series. And thank you everyone for attending, especially those of you who are in Europe where it is 8 or 9 o'clock. I just finished up an internship at IBM Research in Zurich, and I see a few of my colleagues there have joined. So thank you very much for taking time out of your evening. So I'm going to share my screen. And so are people able to see my screen?
Yes.
Great. And so as I'm giving the talk, since I'll be looking at my slides, I won't be able to see, I think, if people have raised their hands. So feel free, if you have any questions at any point, to just unmute and go ahead and interrupt me. And one last thing I want to do. Whoops. I'm trying to get the laser pointer. So if I need to point to anything on the screen, and you're seeing the laser pointer?
Yeah.
Yes.
Yes.
Yeah.
It's visible.
Okay.
It's
Great.
small, but visible.
So I will be talking today of some work we've been doing across two separate papers on differentiable trees and compositional generalization. And so for those of you in the VSA community, we can actually discuss vector symbolic representations and what that actually gets us in terms of machine learning and artificial intelligence. And so I'm a PhD student at Johns Hopkins University. And this is done with colleagues and collaborators at Microsoft and the University of Edinburgh. And so the two papers I'll be discussing today, the top one is the more recent one, which I'll be presenting at NeurIPS next month, just in a week. And that's called Compositional Generalization Across Distributional Shifts with Sparse Tree Operations. That is predominantly what I'll be discussing today. And when needed, there are some slides I'll introduce that come from an earlier paper of ours called Differentiable Tree Operations Promote Compositional Generalization, which was published at ICML last year. So to get started, I want to sort of present a motivating example of why we even want to go down this route in the first place of differentiable trees, differentiable operations, and why some other neural network approaches seem to be failing. Even ones that have a sort of a tree inductive bias in them. So here we've got two trees. The first one, you can think of this as very similar to a very basic type of semantic parsing task, where you're given a tree in the active voice, the dog ate the treat, along with the constituent structure and non-terminals. And you want to convert it to its logical form, which just raises the verb to the left child of the root node, and it combines the arguments into their argument structure. And so here it is presented as a tree. If you wanted to linearize it, you could use a parentheses representation to be able to feed this to a neural network that is only expecting sequence as input and output. So here are the trees and their linearization. And so we can use a tree neural network, say a tree RNN, which, if you're not familiar, is similar to a left to right LSTM, actually more similar to a bidirectional, one from the left and one from the right, where you have two RNNs, and depending whether you're a left child or a right child, you get passed through a different network. And you can use this to build representations that are sensitive to the constituent structure of whatever tree you're encoding, which is good. We think that sensitivity is an important aspect of human linguistic competence, and we want it in neural networks. And that also shows a benefit of why you would want, say, a tree neural network over a linear one. So here I've shown just a tree RNN processing this noun phrase, the dog. And when this noun phrase appears here in the sentence form, or it appears here in the logical form, the representation at noun phrase will be the same regardless of where in the tree it is. So either if it's the left child of the root or if it's embedded further down, it doesn't matter. The representation of these subtrees are going to be the same because they're processed in the same bottom-up manner. Now, when you get to the root node, the representations will be different because the trees as a whole are different, but the constituent, regardless of where it appears in the tree, will be the same, and that's an important attribute. Now, if you look at these linearized forms, say if you fed it to an RNN or a bidirectional RNN, you're very unlikely to get the same representations for these substrings because they're dependent on the content that appears to the left or the right. And so isolating the representations for these individual constituents is very difficult, and you're very unlikely to come up with the same representation if constituents appear in different places within the trees. So that's motivation around why we would want to be sensitive to tree structure. But the question is, well, so does this tree RNN work? Why don't we just go forward with that? Why did I even have to do this research in the first place? And so you can do sort of tree encoders. That's what appears on the left. And, you know, I sloppily just inverted it 180 degrees, but you can also produce an output tree in a top-down fashion. And so what's important here and what we care about is that regardless of what appears in this argument position in the active sentence, the same constituent appears as the left child of the argument. And we want to be invariant to anything that appears within this green box. It's just really being copied over. It's very simple. It's just changing positions from left child of the root to the right left child of the root. And yeah, so we want it to work regardless of whether new words appear or there's different substructure within these green boxes. It's just a simple movement operation. And so the types of distributional shifts we might care about, for instance, our lexical generalization, where we've now changed it from the dog to the wug, where wug is a word that was either only encountered once during training or even zero shot was never encountered during training. As well as structural generalization, which means that you see new nodes at test time that were never encountered during the training distribution. So here we've got a much deeper tree, much more complicated structure by adding a bunch of adjective phrases and to the noun phrase. And so just to motivate why we did this work, here is a couple data sets. The specifics of them are not important. They're basically tree-to-tree transformations. And when a network like a transformer LSTM expects a sequence, we linearize it with parentheses. And now we're looking at lexical out-of-distribution generalization and structural out-of-distribution generalization. And we see that none of the networks really perform well. So even these tree-to-tree LSTMs or tree transformers that are sensitive to tree structure, they're very good at learning tree distributions IID. They fail when we start to test on out-of-distribution generalization. And so that's what kind of motivates this work, is that it's not enough to simply have representations that are sensitive to tree structure, but also that the operations that are performed also over those trees must also be sensitive to tree structure and not just be sort of random neural network learned linear transformations. And so, yeah, why don't these tree models generalize? It's because they have tree representations, but they don't have tree operations. And so what we're going to introduce here in our work is a mix. We both have tree representations, but we also have operations that are systematic. And we're going to introduce an architecture that puts together these systematic operations with a learnable neural network that will learn how to sequence the selection of operations and arguments to do something akin to program induction. So we'll be looking at just 3 tree operations. So it's a very small sort of domain-specific language, but very general purpose. Left child, right child, then construct. So left child simply extracts the left subtree and moves it up to the root position. So determiner now becomes the root node and my becomes the left child of the root. Similarly, write just extracts the right subtree. And construct is slightly more complicated, where it takes in 3 arguments. It takes in the tree that should be the left child of the new tree, a tree that should be the right child of the new tree, as well as some symbol to place at the root. And while these 3 operations are very simple, along with conditional branching and equality checking, those 5 operations altogether are Turing complete. So any function that is computable should be able to be expressed with these 3 operations, as well as the conditional branching and equality checking. I didn't discuss those 2 on this slide. They'll be introduced later, and that's going to be the actual learnable part of our network. But for now, the 3 operations that we want to sort of create a domain-specific language for are left child, right child, and construct. And for those that have been around for a minute, this used to be familiar from expert systems and GoFi, and in Lisp, this was referred to as car, quitter, and cons. But the feedback I got after the first paper was that left, right, and cons is much easier for people to understand. So how do we perform tree operations in vector space? The first aspect of this is going to be showing you how to embed trees in vector space in a way that we can then perform the tree operations in vector space. And we're going to be introducing a new representation scheme in order to do that. So the representation scheme that we've developed is called sparse coordinate trees. This is equivalent to a TPR, which is what we used in the first paper that we presented at ICML last year. And then the newer work, we've developed this representation system called sparse coordinate trees, which is mappable to a TPR and vice versa, but it is much more memory efficient, as I'll show. So we start with some tree with its associated tokens in different positions. And I've shown here also after the period the Gorn address, which is a way of indexing positions within a tree. So we start by indexing at 1, which means this here is the root node. What this 0, 1 means, reading from right to left, 0 and then 1. The 0 means we are the left child, and then the 1 means that's the end of the encoding scheme. Similarly, 1, 1 means we are the right child of the root node. And so similarly, to be the right left child, you get the 1 here for being right child, the 0 for the left child, and then the 1 means to stop reading. And so this is a representation of the sort of the tokens that would be in each node position, along with the addressing scheme for that location. So the tokens are just your regular fillers in TPR speak, are just token embeddings. You can look them up like a regular PyTorch embedding dictionary. And our tree positional indices are going to be represented by these Gorn addresses, but then just converted to their integer form. So we see here that person, which is the right child of the root node, has a Gorn address 111, which means its tree positional index is 7. And so in sort of VSA terminology, we do binding by just looking up, table lookup, over keeping a token in its value here, like say determiner phrase, is lined up with integer 1. Which means that determiner phrase appears at the root of the tree. Similarly, the is lined up with position 2, which means it's converted to 0, 1, 0, which means it's the left child of the root node. And so binding a new node simply means adding a new vector to our values, as well as a new index to our tree positional indices, and keeping those lined up. And the reason we called it sparse coordinate trees, if anyone here is familiar with sparse matrix representations in NumPy or scikit or PyTorch, is that there is a representation scheme called a coordinate list. And so these are sparse coordinate trees developed from sparse coordinate lists. And so that's the scheme for how we represent our trees in vector space. But that also leaves open the question of how do we actually perform an operation in vector space that is sensitive to the tree structure. And this is sort of what separates this work from, say, a tree RNN, where you're sensitive to the structure, but you have no way to, say, extract the left constituent from a given tree. So here, this is the orange arrows show the output of performing the left operation. So we see, for instance, that determiner phrase gets moved to the root, the gets moved to the left child of the root, and then we see that the right child of determiner phrase needs to get shifted over to the right child of the root. So it actually sort of crosses these tree boundaries where it's not just everything moving up, some nodes need to move to the opposite side of the tree as well. And so here is our tree represented in a sparse coordinate tree format. And first thing we do is we perform an even mask. The reason for that is we want to extract all the left children. And we see if we look at this subtree here, every node has a 0 in the rightmost position. And if we look at the other nodes, all of them have a 1 in the rightmost position, which means that by using an even mask, the resulting indices will be all of the left children of the root node. And then we perform a right bit shift operation to move all of the nodes up one level in the tree. And that gives us a new positional indices for all of the matching values. And then we perform a cleanup where any node that has a tree positional index of 0 is removed. And then we just squish all of our values and remaining tree positional indices together. And what that would result in is we now have a sparse coordinate tree where determiner phrase is in position 1, which is 0, 0, 1, the root node. And for instance, fun, which used to be in positional index 10, is now in positional index 5, which corresponds with the right-left child of the root node. I want to stop here for 1 second in case anyone has questions on the differentiable operation or the sparse coordinate tree.
Let's say ask the public. Do we have any questions? Then Paul, please continue. So we will have discussion by the end.
Great. And so I'm using these bit shifts for, whoops, 1 second. I just got a pop-up. I don't know if that showed for you. I think that's fine. We're using these bit shifts. Is that differentiable? So a right bit shift is actually very similar. It is identical to this permutation-ish matrix. It's not exactly a permutation matrix because all of the odd positions don't get permuted, but it's basically a permutation matrix over the even indices. And it just moves them sort of a right bit shift in terms of row to column mapping. And that means in the forward pass, the vectors will get moved from some rows to different rows based on the permutation. And in the backward pass, the gradient will get permuted in the opposite direction. And so this right bit shift is identical to this permutation-ish matrix, which means that it's fully differentiable. Except by performing the right bit shift operation, we never needed to actually materialize this permutation matrix. And so one of the issues we were dealing with when we were using tensor product representations is that the TPRs themselves are very large. And we could perform, say, this differentiable left operation using dense matrix multiplication. But as the size of the TPR grows, as the size of the number of nodes that we can represent grows, the size of this permutation matrix grows exponentially, and we were running out of memory. And so I just realized I wanted to go back and talk about this for a second. So comparing the sparse coordinate trees to a TPR, one of the main differences is that a TPR, if you're using dense orthogonal rolled vectors, is that if you have a tree with just a single node filled, the amount of memory it takes up is the same as a tree that has every node filled. And that is problematic if you are only dealing with small trees. And so the sparse coordinate tree representation It is similar to TPR in that as the dimensionality, as TPRs, as you keep performing outer product, the dimensionality of your whole structure grows in size. That's true for sparse coordinate trees as well, where you, like a classic symbolic tree, the memory used by the tree grows proportionally to the number of nodes that are filled. And so if you only have one node filled determiner phrase, you only need to keep track of, say, here's four floats and one integer for the position that it fills. Whereas the TPR, this tree positional index would be a dense vector, and you would perform an outer product. And that would grow the memory usage of just having one node filled to the same memory usage as having all of the nodes filled. And so we got here by first going from dense orthogonal roll vectors to using sparse orthogonal roll vectors, which were the standard basis, just your canonical basis of one of different dimensions in vector space. And so then we were using a sparse representation of the TPR, and we realized it was even more efficient to just manually keep track of the values in the tree positional indices. And so going now to differentiable right is very similar to the differentiable left, except we changed the mask. Here, before we were going using an even mask. Now we're doing an odd mask greater than 1. So the odd mask will give you everything with a 1 in the rightmost bit, which also gives you back the root node. And that's why we do an odd mask greater than 1. And that gets rid of the root node and keeps only everything that is a right child of the root. And then the bit shift moves everything up one level in the tree. So construct is a little bit different because it takes in 2 arguments, but it is effectively very similar. But instead of a right bit shift, you take in your left argument and you perform a left bit shift to move everything down one level in the tree. And to perform for the right argument, you do a left bit shift and then you add 1 to move everything from being to the left subtree to the right subtree. So that's an example of how we embed our trees in vector space. It's an example of how we perform our tree operations in vector space. But really what we want to do is to be able to learn programs. We want to learn sequences of operations and argument selection and make it all differentiable end to end. And so in order to do this sort of superposition program induction, we need a way to make our argument selection and operation selection differentiable. So we do both of these things using soft summation, similar to an attention mechanism. So here we've got a memory with 3 trees in it, and we need 4 arguments. We have the argument that is fed into the left operation, the argument that is fed into the right operation, and the argument that is the 2 arguments that are fed into the construct new tree operation, meaning the left child and the right child of the construct operation. And to get each of these, we just do a soft summation. So the tree that is the left, that is fed to the left operation is just a weighted blend of the 3 trees in memory, here weighted by alpha 0, alpha 1, and alpha 2, where these alphas are just a softmax distribution over the trees in memory, and they all add up to 1. And so we do the same thing here. There's 4 softmax, and that gives you the distribution of this for the summation parameters to use for the left tree, the right tree, and the 2 construct trees. Similarly, for operation selection, it's again a weighted sum where we just do a softmax distribution to get weights for the left operation, the right operation, and the construct operation. So here we have 4 arguments. Here there's only 3 operations to select from, and you see that the weight that's shared between cons left and cons right is the same, W cons. But the trees that are fed into those operations are different. So if we put all of this together, what I just described, we call the differentiable interpreter. And that produces, through the function that I just showed, the operation selection, it creates a new tree, which we write to memory. And these two things feed into the agent, which is where the learnable parameters of our model are. And it's the agent that does the selection of, say, these alpha parameters for argument selection and the W parameters for operation selection. And because our system is fully differentiable, we can have our agent just be parameterized as any sort of neural network. We'll use a transformer. And it allows the learning of programs to be done in a fully differentiable manner end to end. And so there are two variants that I'll show results for. The first is the tensor product DTM. And so that uses TPRs in order to represent trees in vector space, as well as to perform the left, right, and cons operations. And then the sparse coordinate tree DTM, which we'll call the SDTM, which uses sparse coordinate trees for representing the trees in vector space and the bit shift and masking operations to perform the differentiable structural transformations. And so just a few details about the agent. We use a transformer. The inputs are a representation of the memory, which is this line right here feeding into the bottom of the agent, and a representation of the state, which is the recurrent connection feeding back into the agent. And then the output for the agent is a softmax distribution over the arguments, a softmax distribution over the operations, as well as an updated state. So those first two things are fed to the interpreter. Those were the alpha and W's that I showed on a previous slide. And then the updated state is fed back in via this recurrent connection at the top of the agent. And so I won't go more deeply into the agent's architecture, but I do have a slide at the end if there's time and questions, sort of expanding out the agent, or you can just take a look in the paper where there's some more details. And so one thing that we needed to handle is that our trees are of variable shapes, depending on how many nodes are filled. And we needed a way to get a fixed vector representation for our trees so that we could feed it into our transformer. And so we compress our trees using a technique called pooling by multi-headed attention. Compressing the trees was not necessary when we were using TPRs, because we could just do a linear transformation, because whether you had one node filled or 10 nodes filled, the dimensionality was the same as if all of the nodes were filled. But now that we're using the sparse coordinate tree, we needed a way to deal with a dynamic number of nodes, but get a fixed dimensional output. And so the way this works is we take our sparse coordinate tree, as well as the tree positional indices, and we concatenate them together. So you have a set of floats for your filler embeddings, and then a set of bits for your roll embeddings, and we just concatenate them together. And then there's a set of query vectors that exist just off to the side. The query vectors are not generated like in a transformer from the sequence itself. Rather, they're just a set of learnable parameters. And the query vectors are issued. So these this concatenation of our fillers and rolls, or our values and tree positional indices, are used as the keys and values. And then these query vectors are used to match against the keys. And then there's a soft summation, which gives you a fixed dimensional output, regardless of how many rows there are in your sparse coordinate tree. But there's another issue, which is that our trees grow too quickly. And so we can see that here highlighted in orange is that because we're taking a weighted blend, we're never actually, say, just performing the left operation on tree 0. If anything, you're performing the left operation with 0.999, on tree 0 with 0.999, but that means you still have some weight applied to, say, performing the construct operation on tree 2. And so we never have this sort of hard discrete decision, which means at every step of the operation of our differentiable tree machine, we are performing a construct operation on the largest tree in memory. The construct operation and the largest tree of memory may both be downweighted by very small coefficients, but those are still there, which means our tree is growing one level of depth every operation, which is exponential in growth, and that's going to cause an issue with memory usage over time. So to visualize this as an example, let's just say you have one tree in memory. It's just the word the, and you perform cons. So you get the, and then you perform cons again. So the second cons, it has two inputs now. You've got the larger tree as well as the smaller tree. And so the smaller tree, the original input, produces the two thes that are in the middle of the tree, whereas the second tree, the, produces the four thes in the bottom row. And you see that after, say, 10 operations, you're going to have a tree of depth 10, which is 2 to the 10 nodes filled, and it's going to grow too large and too quickly. So to handle this, we do a form of tree pruning, which is very trivial, which is just that after you produce a new tree, you just drop some nodes. And so you can think of this as sort of a channel-wise dropout, where you've got your sparse coordinate tree, and then you're just dropping out entire rows instead of just dropping out random dimensions within a single row. And so I'm going to discuss some results now, and if anyone has questions about everything I've discussed about so far, feel free to unmute and ask. And so one thing we wanted to look at in our results was this idea of looking at unified neurosymbolic systems versus hybrid neurosymbolic systems. And so in a unified neurosymbolic system, computation can simultaneously be viewed as neural or symbolic. So I introduced a way to perform a left and right operation using bit shifts. And that tends to seem like a sort of a symbolic approach. But I also showed the permutation matrix, which is just a linear transformation. And that's the way of viewing the same operation via a neural lens. A hybrid neurosymbolic system, on the other hand, is a system where the neural components parameterize symbolic components. So you can think of, say, some sort of more classic Bayesian context-free grammar learning system, where the actual probability distributions are parameterized via neural networks. But at the top level, the system is itself being sort of restricted to be a symbolic system. And so one thing that we get from using a unified neurosymbolic system is that we can generalize like a symbolic system, but we stay flexible like a neural one, because any operation can be simultaneously viewed as either neural or symbolic. Whereas hybrid neurosymbolic systems, they generalize like symbolic systems, but because they have these core bottlenecks where computation is forced to go through a symbolic route and cannot be viewed as a neural network or a linear transformation, they become brittle and fall apart and are less flexible and scalable. So the baselines we'll be looking at our results are just a regular transformer. And so whenever a tree is used for input or output, we'll do it in parentheses in order to linearize the tree. We'll also be looking at some cases of tree inputs and outputs, and I'll show you how those are represented. A relative universal transformer, which was introduced in a paper suggesting or showing that the relative universal transformer has better out of distribution generalization than a regular transformer, but it is still a fully neural system, just uses relative positional embeddings in a universal transformer instead of having different weights at each layer. NQG is an example of a neural quasi-grammar learning. That's what the NQG stands for. And that's a system that uses a neural network to parameterize probability distributions, but is using a grammar induction method. And so that's an example of a hybrid neurosymbolic system. And then we'll also be looking at baselines from the original DTM paper on just, I think, one data set, which was the tree-to-tree LSTM and the tree transformer. which I introduced very early on. So the first data set we'll be looking at is called active logical. It goes in either direction. So you either get a sentence in this active voice and you have to convert it to the tree in the logical form, or you get a tree in the logical form and have to convert it to the active voice. And so the purpose of this experiment was to show that our new SDTM, sparse differentiable tree machine, was not a regression on the performance from the original TPR version. And so I had shown earlier in one of the first slides that the tree transformer, regular transformer, and the tree LSTM, none of those have good out of distribution generalization on this data set. And now looking at the models we're considering here, when we look IID, we see a transformer and the RU transformer are both able to learn the training distribution very well. Whereas we see our hybrid neurosymbolic system, the NQG, is having trouble learning the IID data set. And that gets to part of the flexibility of the unified neurosymbolic systems, which is that at the end of the day, you can just ignore the symbolic part. It just looks like a neural network. It's got these permutation matrices embedded inside of it, but that's just moving some information around. It's shifting rows around. And it sort of has this fully end-to-end neural pathway, which should make it good for learning IID, like we see from a transformer and RU transformer. But when we look at these two models that are good at learning the IID data set on distributional shifts, zero-shot lexical generalization, which means at test time you encounter a word you've never seen before, or structural generalization where you encounter nodes you've never seen before, we see that these more traditional neural network approaches have very poor generalization. And so I'll be presenting results now from the original DTM, the TPR one, as well as the SDTM, sparse coordinate tree, differentiable tree machine, as well as STTM with the pruning method to reduce the memory consumption. And so all three of these models are able to learn the training data, as well as have very good performance on zero-shot lexical generalization and almost perfect structural generalization, except for the method that uses pruning, which drops slightly, but not by too much. And when we look at the computational statistics behind these heuristics, we see that the SDTM is using almost an order of magnitude fewer parameters, 70 times fewer parameters. And we look at the memory usage, we see going from the original DTM to SDTM, drops memory usage by a little over 3 gigabytes. And then going from SDTM to the pruned version is dropped by an order of 5. And so we've got an order of magnitude less memory usage and almost an order of magnitude less parameter usage going from our original DTM to the SDTM with pruning, as well as a 34-time speed up. And so the SDTM will allow us to look at trees that have much larger depth, as well as a variety of sequence input and output operations where the original DTM was just too inefficient to test on. And so we see the SDTM with pruning does have a minor drop in structural generalization, going from 100% to 95%. But with that drop comes huge increases in the throughput of our model. And so active logical shows the deficiencies of the regular transformer and RU transformer, as well as the hybrid neurosymbolic model, but it was handmade to work with the DTM architecture. So it's not surprising that DTM does well, and we wanted to look at more complicated data sets, created prior to DTM by other people. And so there's a data set called 4 to LAM, which is a program-to-program translation data set where you're given an abstract syntax tree in a programming language called 4, and you want to convert it to an abstract syntax tree of a programming language called LAM that has a different grammar. And so this was introduced, actually forgot the citation on this slide, by Chen et al. In 2019, I think. And that's the paper that the tree-to-tree LSTM was introduced with. And so when we look at the results, we see IID, the transformer, RU transformer, and SDTM are all able to learn the IID dataset perfectly. NQG, we trained it for 7 days on, I think, an A100, and it still was going to take weeks more. So we just decided that we didn't have the resources. And so that goes to show another advantage of these unified neurosymbolic systems is that they're more scalable and flexible because they get to leverage all of the benefits that we have from fully neural systems in terms of parallelization and skip any sort of symbolic bottlenecks that may slow down your inference. And when we look at zero-shot lexical generalization, which means at test time, a new variable is introduced, z. So in these trees, we see that we've got x's and y's here. This is saying, y equals y if, x is less than 1. Weird language, not actually important to know the specific semantics of it, but that we've got these two variables, x and y. And then at test time, we see a tree that has a new variable z that is just a randomly initialized embedding. It was never seen during training, so the embedding is random. And we see that the SDTM has a 60% accuracy on this zero-shot lexical generalization. And so I want to highlight this 60% because it is clearly better than 3%, but it is still far from being perfect. And this does introduce a deficiency in the differentiable tree machine, which is that the agent that we use is still a transformer. And by having the whole model go through this differentiable interpreter, we hope to be able to help the agent, the transformer, learn to be invariant to these different distributional shifts. However, it's not guaranteed. And so in this case, in some set of examples, in some contexts, the transformer performs well, and that's why we get 60%. But in 40% of the context, the introduction of a new variable sort of messes up the sequencing of the operations and the arguments to select, and the model does not perform the correct transformation. And so the two data sets that I just showed results for are both tree-to-tree data sets, but we can also process sequence input and output, which is important for testing our method on a wider variety of data sets that were pre-existing in the literature. And so the way we do this, to embed a sequence as an input of trees, what we do is we take that input sequence and we just set every token to the root node of a different tree. So instead of initializing our memory with just the input tree, in this example, we initialize our memory with 5 input trees, each one just having the root node filled and nothing else. And in terms of embedding outputs, sequences as outputs, obviously, if you have a parser, you can parse the tree or parse the sequence into its tree. And if you don't have a parser, which usually you don't, you can just take the input sequence and embed it in a tree at whatever level is necessary to have the number of leaf nodes as long as the input sequence. So we see here we've got 6 nodes in our output. So we had to embed that 3 levels deep in the tree because at the second level, we only had 4 nodes, which wasn't enough. And so we went to the third level so that we could embed all of our words. And so we call that left-aligned uniform depth, where all of the tokens in the output are just aligned to the leftmost portion of the tree, and then they use the same depth. And yeah, when we use sequence inputs, it means that we can drop the left and right operations. So now our trees or our differentiable interpreter is only performing one operation, which is construct, which also makes the space of programs that can be learned much smaller. And there are some tie-ins with the minimalist program if we have any linguists in the room, where merge is suggested to be the only operation that is needed for human language processing. So the next data set we'll be looking at is called a GeoQuery. It's an example of a seek-to-tree data set. And it is a very weird data set. I think it's from the 90s. You get these sentences like, what is the capital of the largest state in the M0, where M0 is sort of an abstract variable, could be, in the country or in the United States. And then the output is an SQL command, which maps to some sort of database where there's information about cities and different data that is relevant. So this is, an example of a very classic semantic parsing task. We're trying to go from natural language to an SQL query. But there's some weird things with GeoQuery, and as I'll show in the results, none of the models do particularly well. And so when we look IID, we see that the transformer and RU transformer are performing the best. I don't think that's particularly surprising, since neural networks are known to do very well IID. And it's when we turn to out of distribution generalization that we tend to see issues with regular neural networks. And then we see a drop for NQG and SDTM, but kind of similar results. When we look at length generalization, we see that none of the models are performing very well. I had put two results here because there was a replication study for NQG, and they were unable to get the 37% that the first paper had suggested. We see that SDTM is still a little bit behind the other models. It's also true on template generalization, as well as TMCD, which is just another form of distributional shift, using compounds instead of individual words. It tries to create a training and test set with bigrams that are as different as possible. And so this goes to show that SDTM is, it's not perfect. It's falling far behind the regular neural networks, the transformer and the RU transformer, as well as NQG. However, all four of these models are far from ceiling performance. They're all failing to even learn the training distribution. And GeoQuery is a very strange data set. It only has 600 samples, I think, in the training set. And the natural language sentences were not generated from some grammar. Rather, they were just written by hand. So there's a lot of variation between the inputs. And it is a very difficult task, as we can see here, that none of the models we've looked at perform very well. And so it's possible that with given more data, NQG and SDTM would excel, because they sort of do have these compositional symbolic components. But since the data set itself was not generated from some underlying grammar and is instead a very small data set with very strange input sentences, we see that these models do not perform well. And the final data set that I'll be showing results from is SCAN, which is a sequence-to-sequence data set. You can think of it as either semantic parsing or translation from human language to some language that a robot executes. So an example sentence would be walk thrice and look right. And then the output is walk, 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 turn right and look. And so we embed the input sequence into memory as just a set of trees. And the output is embedded into a tree either using a parser or using this left-aligned universal depth LOD embedding scheme. And so let's go through the results. Yeah, so we have an IID data set. We also have one-shot lexical and zero-shot lexical versions, as well as length generalization, which looks at test time at sequences that are longer than those seen during training. Template is similar to lexical generalization, but instead of an individual word that's missing, it's sort of a compound template, and MCD, which is again that bigram divergence. And so when we look at IID results, we see that all of the models, except the original DTM, perform very well, which shows an improvement of SDTM over DTM, where the introduction of pooling by multi-head attention, in addition to reducing memory usage, also makes the network more expressible, and it can learn to the scan IID training distribution. Looking at the lexical generalization, we see that for one-shot lexical, neither of the transformers do particularly well, whereas NQG is able to have perfect accuracy. And we see that both versions of SDTM, either with the parse trees or just these universally aligned output trees, does pretty well. And when we go to zero-shot lexical, we see that NQG completely falls apart. It goes from 100% accuracy to 0% accuracy, whereas SDTM maintains its performance. When we look at length generalization, we see that RU transformer is doing a bit better than the regular transformer, which is evidence that the original RU transformer paper had suggested. Although, as we've seen throughout the experiment, RU transformer is not much of an improvement over a regular transformer. NQG has very good length generalization, as well as the SDTM with parse trees. But when we use the left-aligned uniform depth trees, the length generalization falls dramatically. In terms of templates generalization, the transformer variants do very well on this actually, whereas NQG does not. And our two versions of SDTM do perform very well. And finally, when we look at MCD shift, we see that only NQG does well. The rest of the models are still struggling with this type of distributional shift. So I showed a bunch of results across a bunch of different models, across a bunch of different splits. I'm all going to consolidate all of that now and just give you a better overview. Sorry, I don't know what that transform animation was. So here we've got sort of a spiderweb plot showing the different distributional shifts, and the results are going to be averaged across all of the data sets. So when we look at the transformer and the RU transformer, we see that they're very well IID, and they do very well on template generalization, but they're very weak on zero-shot lexical, one-shot lexical, MCD, and length/structural generalization. When we look at NQG, we see that it is not quite as good at IID. And that's one of the points I made about a hybrid neurosymbolic system, is that because they go through these symbolic bottlenecks, they tend to be more brittle than fully neural systems. However, they do much better at MCD than the regular transformers, and they do better at length and structural generalization as well as one-shot lexical. Finally, when we look at DTM, we see that it performs almost the same as the transformer and RU transformer, IID. That's because there's this pathway through the network where you ignore any of the symbolic stuff and you're really just looking at it as a neural network. When we look at MCD, we see that it does not perform any better than the transformer or RU transformer and falls a bit shy of the MCD, or falls short of NQG on MCD. Looking at template, we see that DTM does a bit better than NQG, but is still falling short of the regular transformers. I think these results are interesting, suggesting that transformers are sufficient for template generalization, because across the few data sets we looked at, regular transformers seem to do quite well on that distributional shift. DTM also does better than NQG on length and structural generalization. It matches NQG's performance on one-shot lexical, where both transformer variants are getting less than 10%. And it has very good zero-shot lexical performance, where none of the models are able to get over 0%. And so this is sort of an overview of all the different distributional shifts averaged across the data sets, looking at the different models. And so future directions that we want to take this work. The first is that DTM is non-autoregressive. You get some input sequence in or some input tree, and you produce an output tree or output sequence. But the output tree and output sequence are not generated, say, token by token. You're not using teacher forcing or conditional probability distribution in order to learn the whole sequence. Instead, you're just producing the entire sequence at once. And there's work showing that learning transformations in a non-autoregressive setting is much more difficult than learning in an autoregressive setting. And so to address that, we want to create an architecture that leverages DTM, but does so in sort of a left-to-right autoregressive fashion. And so we're working on a differentiable shift-reduce parser, which will be sort of an autoregressive language model variant that is similar to DTM, but works in a sort of left-to-right fashion, which will allow us to also look at language modeling data sets. And this combines the differentiable trees that I've introduced here, as well as some work on differentiable stacks that the community has done. So thank you, and I hope there's some time for some questions.
Thank you, Paul. Thank you, Paul, very much for your talk. Well, yeah, it was quite technical, and I think, at least for my part, I need to read paper in details to ask some specific questions. But I maybe can start with the really high level. So, and I want to apologize if it will be too naive question or so. Well, you mentioned, I mean, you always compare with different transformer architectures, but what I'm thinking about is how such hybrid systems like Gen AI systems like Open AI systems solve similar tasks. So not just a particular architecture transformer, but for example, how ChatGPT would solve such tasks. I mean, and how your DTM would compare to the performance of Gen AI systems.
Yeah, just, am I muted? No, okay. So just to clarify your question, are you asking about literally feeding the samples into, say, ChatGPT, or
well,
having
I guess
ChatGPT produce a program that produces the transformation?
I guess systems like ChatGPT, so they use quite well a hybrid, transformer and some other stuff to parse input and trees to transform the programs from different languages. So so my question is how your architecture is compared to this kind of functionality.
Yeah, so if you are looking at ChatGPT from say this hybrid perspective, maybe GPT has this Python interpreter mode, and that's sort of a hybrid component where you've got the underlying language model, which is a fully neural transformer, and then it's producing some code that is then fed into a Python interpreter, and then the result is returned. The issue with that sort of technique is that there's no way for the model to learn directly from the output of the interpreter. So the program is executed, it produces some result, and there's no way to get a gradient so that the model produces a different program in the future if it got that result wrong. And so if there was a way to, say, create a differentiable interpreter for all of Python, then you could use that so that GPT could produce programs, get outputs, and then actually backprop through the programs and update the parameters of the underlying language model using the gradients from the differentiable interpreter.
Mm. Okay.
I think you could also probably try to train one to create better programs using maybe something like reinforce or some gradient estimation techniques. But I think those have issues with scalability, whereas here it's just sort of a first order gradient is just going through the interpreter. So the agent is able to update its parameters from that signal.
Okay, thank you, Paul. So I will digest it in the meantime. So, but Tony, so you raise your hand, please.
Yeah. Thanks for that, Paul. Really interesting talk, and I liked all the test cases. So I was trying to understand the details of what you're doing. One of the questions I had was that all of the tree positional indices that you showed were discrete bit strings, but if you're using those in a system where you're passing gradients, then I'm assuming they exist in a continuous space. And what space is that? Is that like a vector space, or is that the integer space like 5 and 6 and?
So the tree positional indices are always bit strings and fully discrete. And so, you think of this like blending that occurs when using, say, a TPR and HRR. And what we're doing is you can sort of push the blending to the filler space or the roll space. So you can say, have the fillers are blended with fully discrete rolls, or the fillers are discrete and the rolls are blends. And what we're doing here is pushing all of the blending to the filler space, and where the rolls stay these sort of fully discrete positional indices.
Okay. Okay.
So there is, for example, nothing in between a left and a right.
Yeah.
There is sort of, whereas if you have two orthogonal vectors, you could sort of find the point in between them and say this is a blend of left and right. That doesn't exist here.
Okay. Okay, I think I get that, but that makes my other question even harder for me to understand, and that's, can you explain more about how the multi-headed attention pooling keeps the associations between the tokens and their tree positional indices?
Yeah, let me get to that slide. I think it's before this. Yeah, so the reason that we needed to, that's basically what this concatenation is. So you can imagine that you have some sparse coordinate tree with just a bunch of words, and you perform query matching, you turn these words into keys and values. The issue there is that pooling by multi-headed attention is permutation equivariant, where if you, in fact, the invariant to the order of keys and values. So if you have a subtree of the man saw the dog, and then a subtree of the dog saw the man, if you have no positional information, those will give you the same representation, but the sentences are very different. The dog saw the man versus the man saw the dog. And so to deal with that, we wanted to add some positional information into this sort of pooling by multi-headed attention. And instead of adding, say, positional vectors like you would in a transformer, just your sinusoidal or learned ones, we wanted our positional information to be sensitive to the nodes in the tree and where those positions appear. And so what we do is we take, say, these fillers here, and we concatenate them with their roles. And so the pooling by multi-headed attention is sensitive to both the content of the filler as well as the role that it is in, because those two are concatenated into a single key. And so the man saw the dog versus the dog saw the man, those have the same fillers, but the filler for, say, the word dog has a different role position concatenated next to it. It's got a different order of zeros and ones, and that allows the output to be sensitive to the position that the word appears in.
Okay, so different attention heads then might pick out different parts of the tree. Is that how it works? So there's not. I'm trying to understand whether. So when you're pooling it by multi-headed attention, what I'm assuming you mean you're doing some sort of weighting by attention of the individual vectors, where each vector is the concatenation of a token and a position. So it's like you're doing a weighted sum of those vectors. Is that correct?
Exactly. So our tree could have different number of nodes. The simplest form of pooling is just taking the average of them, where every coefficient is equal to the same, which is 1 divided by the number of nodes that are filled in your tree. And so this is just a way to be slightly smarter and do a weighted sum instead of an average.
Right. Yeah. Yeah. What I'm having trouble seeing is how that keeps the association that, dog is in position 1 and cat is in position 3.
So I think I maybe understand what you're trying to ask. These are fed into. 1 second. I'm going to share my full screen so I can look at the slides more quickly. I think what you're asking is, so here is, these are what's fed the sparse, the compressed tree is what's fed into the agent. We still keep track of the full tree in memory. That still exists. So the agent just has a tokenized version of it. It's been compressed. But when the interpreter performs operations, it doesn't perform operations on that compressed tree. It still has the full tree in memory. It's just the agent now says, okay, use tree 1 with coefficient 0.4. And then we go to memory and we get the full tree, which still has its, where dog is and what node dog is in. And we perform the operation on the full sparse coordinate tree in memory. We just needed a way to shrink it down into a fixed dimensional input to feed into the neural network.
Okay, that helps. Thanks.
More questions, please?
Can I add a little bit to that response?
Sure. Cool. Yes.
Hi, Tony. Long time no see.
Hey.
So to the extent that we have the symbols serving as values and the positions serving as keys, the query sort of unbinds that structure by taking its dot product of itself with the various positional encoding keys. And so it could hunt for certain kinds of positions and pull out the symbols residing at those positions. And so it is kind of like an unbinding of the material in the tree. The only real difference is that the coefficients are not just the dot products of the query with the key, but they're the softmax of them. But I think of it as sort of like a selective extraction of the elements in the tree selected by position and weighted accordingly. But as Paul said, this is a way of sort of giving a compressed synoptic characterization of what's in the memory for this tree rather than serving as the representation of the tree itself. And so when the operators operate on it, they operate on the true encoding where all of the symbol position pairs are intact. Does that make sense?
Yes.
Oh, you agree with that?
Yes. I'm starting to see how it works. That you're keeping both around, and you're using this compressed representation as sort of a guide to what actions need to be taken.
Yeah, precisely. And so the forking is that the control decisions are made are enlightened by these compressed representations of the memory, but the actual operations that the agent selects to perform are executed on the true representations in memory.
And yeah, when you look at, say, the 60% performance on 4 to lamb, I think that's a good example where there's this compression is happening and it's causing the agent to mess up. The agent isn't seeing the full trees, it's seeing this compressed version. And so something about the compression is causing the agent to not produce the correct sequence of operations and arguments. And so there's this sort of shows the dichotomy between the transformer that we're relying on to sequence these decisions, as well as this sort of interpreter memory part, which is explicit and deterministic. It's the agent where all of the learnable parameters reside, and this sort of compression is taking place.
Yeah, you would get perfect lexical generalization if the agent were still making the right decisions about what operations to perform, because their operations themselves are perfectly compositional and systematic. They don't care whether the lexical item is familiar or not. So as Paul was saying, that would be 100% if the agent were still able to make the right decisions as to what operations to perform, given that there are now symbols in memory that it hasn't seen before. which apparently it's not able to do beyond the 60% level.
Yeah, have you thought about are you able to construct like for the various tasks you had, are you able to show that a solution using this architecture, that performs at 100%, that exists? I'm not sure if my question is clear.
So there is some program that performs this transformation.
Oh, right. Yeah. Oh, yeah. No, I get that. But could you instantiate your network that you're trying to train, just say, hey, to perform this, I just need to set these weights to this and this and this, and then it would do it perfectly.
You could just supervising the intermediate steps of the operation and argument selection.
So
is that what you're asking?
Yeah, I'm sort of asking, can you prove that there is a set of weights for the network that you're trying to train that would be able to accomplish the task at 100% performance? Because this is a task that is, it has right and wrong answers, right? So I'm asking, is this architecture, provably sufficient for the task? Is that something that you've thought about?
And the interpreter and memory are sufficient for the task. I guess the question is, what are the weights of the agent that produce the correct program given any input? And for instance, I think if you wrote the program yourself and supervised the intermediate steps of the agent, I think it would probably get 100% accuracy very quickly. Which makes me think that, we haven't looked into sort of a formal proof of the expressibility of this transformation. But obviously, if the network can do it, that's a existence proof. And I think it would probably be able to do it. Again, that's not like the formal solution that you're looking for, but there might be ways to compile the program directly into the weights of the neural network. The hard thing there is that this is sort of where the agent is where the conditional branching and equality checking are taking place that make the whole system Turing complete. And so I'm not sure how to compile those that equality checking and conditional branching directly into the weights of the neural network. But there is some interesting work on RAS, and Paul recently had a paper on PSL. And there's a recent one from Google on Alta, I think. Alta is actually very similar to the idea of what you're asking, and does look at scan and some of these other data sets. And so it's a bit orthogonal to what we were doing, but I think it's a very interesting direction. And I'm not sure, there might be a way to tie together the work that research community is doing with this and sort of directly instantiates the weights such that you do get perfect generalization given some input program.
Yeah. That's like the RASP type systems. That's the type of thing I was thinking of. Yeah, and I've not heard of that one. Alta, you said, from, how do you spell that?
ALTA, and the first author is Peter Shaw.
Okay.
Maybe I'll give a talk in the next season or so on the work that we did on high-level programming languages for programming transformer programs, which might be able to
that sounds
cope with it.
Yeah. I just
and more kind of overuse. Oh, yeah.
Yeah, that was the 100-page paper, right, Paul?
That was, but you just need yes, it was, but you just need to read the first section.
Okay. I read all of it.
Oh, okay. All right. So you know how to program this algorithm then.
Mary, please.
Thanks for an excellent talk. I was happy to see Lisp. My my master's student, soon to be PhD student, and I just recently put out a conference paper where we were translating simple Lisp interpreter into vector symbols. And we were like thinking, well, our next step is to learn over it. And so it's really cool to see that's working here. Have you considered using anything other than a transformer, and are there any particular limitations of the transformer approach that you want to talk about?
Yeah, we originally the uh, the agent was not a transformer; it was an RNN. And when we switched to an agent or the agent to a transformer, it started to work much better. Um, so here is this slide is a mess. This is the agent, and effectively what we realized is that the uh, the agent grows by one token each step, where that token is the new tree in memory. There's too much here to look at, but I would suggest looking at this diagram in the paper to understand the way that we approached it. And we did look at an RNN, and we just didn't see it wasn't working. Whereas the transformer approach, and it is this weird transformer with this recurrent connection. So it's sort of more like an RNN with attention, which we had not looked at. But this allows the agent to avoid having this compressed representation of the state. So I mentioned here that the agent's inputs are the representation of the memory and the state. And if you have an RNN, it means you have a fixed dimension for the representation of the memory and the state. And let's say your program is going, for instance, in for to lamb, I think we go right with 50 operations. So there's 50 trees in memory, and we've updated the state 50 times. And if you have a fixed dimensional representation of that, you sort of run into a big limitation. Whereas the transformer, the size of the agent can grow to accommodate a longer program.
Thank you.
Yeah. And do you have reference for the paper that you were just mentioning? Very
Uh,
relevant to me.
yeah, I could email that to you or drop it into chat.
Yeah, that'd be great. Thank you.
Yeah, I was just going to ask because I haven't found it in my search yet. So Rancher would be good.
Yeah, another question on this slide that you're showing here. So when the agent updates the state, can it also update the memory? Is the memory part of the state that is updated? The memory is where the full representation of the tree is stored, correct?
Yeah. So the agent only produces these softmax distributions, basically to perform this operation on this tree in memory. That is fed to the interpreter via this line right here. The interpreter also gets in the state of the memory. It then performs the operation on the tree in superposition. It writes that back to the memory, and then we compress the new tree and feed that into the agent. So the agent never writes to memory directly. It writes only to memory through the interpreter.
Okay. Okay, but when it does write to memory, that's part of the state that's updated then.
Yeah.
Yep. Okay.
Let's see if we have more questions. It's an exciting discussion, and on my side, I would like to ask you, Paul, if you can really think about giving an overview or an introduction, kind of, to this paper of symbol processing in transformer networks. So that sounds really a great idea.
If you mean this, Paul, the answer is yes. I will endeavor to do that.
Okay, then I will send you a separate email so we agree on time. And Mary has posted a link to GitHub just for you.
Okay, great.
But let's see. So time is 20 past 10 here in Sweden, PM. And I really glad to keep talking to all of you. But I guess it's time to wrap up this webinar anyway. So I was really happy to host you, Paul, and see you, Paul, in the audience. So, and I hope to see you as a speaker next season. So the next season will be a jubileum season, number 10. So you should expect an email from me about the time. But otherwise, thank you very much all for attending this webinar. And we meet in 2 weeks for the last webinar of this season. So keep tuned. So see you next time. Bye, everybody.
Thank you all for
Thanks,
your
Evgeny.
questions and attending.